Alright, hi everyone, you're welcome to my YouTube channel, CTF Electrons. So in this video, we are going to do something that serves as the basic knowledge for wireless communication. Of course, for other things, okay? Now, I can't really see anything on the screen now, but look at this. Now, we all know, at this point, I believe, we all know that this is a sinusoidal waveform. Okay, where we have the highest point, the lowest point, like that. Now, looking at this wave, note I said something. We want to study one of the basics or one of the basic knowledge required to understand and make designs that concerns wireless communication. Okay, so now the thing is this wave we have right here, looking at it on this screen, we can just see the side of it. Okay, we can just see the side of it. But what are we trying to paint, or what are we trying to explain or talk about as a basic knowledge for wireless communication? This propagation of uniform plane wave. Okay, propagation of uniform plane wave. What do we mean by this? How is this one of the basic knowledge required for wireless communication, and of course every other fields? Let me show us this example. So you can see the wave just like what we have on our screen. Looking at it from this side, so we have wave now where we talk about uniform plane wave. Let me start with the plane. What do we mean by plane? Plane is just a flat surface. A plane is just a flat surface. So this wave, where is the plane here? Where is the plane here? Now look at it from this side. All right, now look at the highest point, okay, or the lowest point, but let's work with the highest point. Now, can you see the highest point? Look at it. This is a flat surface. So this flat surface, this is the plane. This flat surface we have is the plane. It's almost like just one line. So you think of it like a wave coming from like in the ocean. That wave, you see, like it's as if it's one big wall from end to end. Sometimes you can't even see the end. Okay, so this is that. Or let me even turn it this way. Yeah, better. Let me turn it this way. So you see the wave coming. This will now hit. This will drop on the beach, on the river bank. This will drop. Another wave come. Another wave come. Like that. So this part, this is the plane. Let's consider that. Okay. And when we say uniform, we mean that it's the same everywhere. Meaning the property of the wave at this point is the same as the property of wave at this point, and it's the same at any point. It's the same. So the wave have the same composition. It's made up of the same thing at each point. So you will say it is what? Uniform. Then this part here, this is a flat surface now. So we say plane wave, because let's mark this thing, or let me mark somewhere in front. Let's mark this point. I think I've marked somewhere before. Okay, marked here. So let's mark that. Okay. All right. That's in the flats. Okay, let's work with that. So now at that point, look at this plane. Okay. So as this plane moves through space, it's being propagated now. So how is a uniform plane wave propagated through space? So that's what we want to talk about. But why is that even important? Now this is important because this concept will serve as basic knowledge in the design of wireless communication, radar system, optical fiber communication, a lot of things. So to see how this is propagated through space, Of course, that includes the relationship between electric and magnetic wave. we will need a mathematical expression to show how they relate. Okay, so with that we need a wave equation. Okay, we need wave equation. All right, so look at this. Yeah, now there is a wave equation that governs the propagation of electromagnetic wave, okay, or how electromagnetic wave travels. To derive this equation, we consider a linear isotropic homogeneous medium. I will explain. Then 2, we assume that the net free charge in the region is 0. 3, we assume that any currents in the region are conduction currents. Okay, now before we begin to derive from Maxwell's equation, because we are going to make use of Maxwell's equation, recall that Maxwell's equation are 4 equations that describe the behavior of, describe how electric and magnetic field behave, okay, or how they interact, not only behave, how they interact, how they are generated and things like that. Now, I hope we are following. We've talked about why we want to study propagation of uniform plane wave. We've talked about that, and we've talked about what propagation is, what uniform is, what plane is, and then wave, of course, and what they all mean together. Okay, and then of course we've said why it's important. And in order for us to now derive in order for us to show the expression or understand this propagation of uniform plane wave, we need an equation which is called the wave equation. Okay, and we've defined the wave equation. Now, in order to get the wave equation, that's what we want to do now. Are we together? That's what we want to do now. In order to get the wave equation, what should we do? Let's consider a linear isotropic homogeneous medium. Recall that in our previous video, we derived the wave equation for free space. Wave equation for electric field and magnetic field. Where is that? Where? Okay, that was done here. We did that here. So this slide is from our previous video, and we've derived the wave equation for electric field, and then the wave, this magnetic, the wave equation for electric field, and then the wave equation for magnetic field in free space. This from the last video. Now in this video, we are going to derive the general wave equation, not just for free space, the general wave equation. So of course the general wave equation that will also consider the concept of free space, or the idea of free space, because this is general wave equation. So with that being said, just like we said in the previous video, the net free charge in the region is what? 0. Net free charge, which is this guy. What are you? Which is this guy. This guy equals what? 0. This from the second condition. Now, for the first condition, we consider what? A linear isotropic homogeneous medium. Medium is where the wave travel through. So the wave can travel through air, through wall, through anything, water, whatever. Okay, so the medium is what we are talking about now. Where will this wave travel through? For us to get the wave equation, let us consider that the medium it will travel through is what? Isotropic. What is the meaning of isotropic? Now, isotropic simply means that at any point, if you measure from any point in the wave, if you measure from any point to any direction, you will get the same value. Are we together? That's the meaning of isotropic. Oh, let's go to another point. If you take from another point and you measure to any direction, you will get the same value. Are we together? So we are saying that, oh, not the wave please, the medium. We are saying that the kind of space that the wave travels through, any point in that space or point in that medium that will take and measure to any direction, we are going to get the same result. To the y direction, same result. Measure to the x direction, same result. That's isotropic. Homogeneous medium. Okay, I'm not saying anything about linear. Let me go with homogeneous first. Homogeneous medium, it simply means every point in the medium have the same property. Every point. It's just like, imagine a cake. Okay, imagine a cake. If you bite from any point, you will get the same taste. That's the meaning of homogeneous. Okay, it has the same property everywhere. Then for linear, that is, the input is directly proportional to the output. The medium's response to the wave is directly proportional to the wave's input. Okay, so I hope we get that. Yeah, so that's literally the meaning of linear now. So the kind of medium we are dealing with to consider the wave equation or to derive the wave equation, the kind of medium we are dealing with is what? Is linear. Is what? Isotropic. Is what? Homogeneous. Good? So the next, we assume that any current in the region are conduction current. So what's conduction current? For conduction current, J equals what? Conductivity multiplied by what? The electric field. Okay, conductivity multiplied by the electric field intensity. So then one other thing we are going to need is this. We have written this before, but let me just put it as a reminder. Magnetic flux equals what? Permeability multiplied by what? Magnetic field intensity. Magnetic flux equals what? Permeability multiplied by magnetic field. Electric flux D equals permittivity multiplied by what? Electric field intensity. We've done that before, but just let me keep that there so you just to recall. So with this being explained, and we have this already, so we'll go back to Maxwell's equation. Of course, we have to make use of Maxwell's equation. It's the equation that describes the behavior and then the interaction of electric and magnetic field. So we'll go back to Maxwell's equation to substitute this guy and this guy. These are the things we are talking about. Okay, I just added this because we will need them. Now, and we are going to use the point form, and I explained why we use the point form in the previous video. Okay, so yeah, because it's just a point now, and the point form is integral. I mean, the point form is what? Differential form. So for simplicity, we'll consider a point, we analyze that point, and then we'll get an equation out of it. So Maxwell's equation. Now let me start with Faraday's, because this is the equation that has the electric field written like this. Okay, for the other it's dots and so on. So let's start with this. And for this, Maxwell's equation, which is the Faraday's law of induction, which states that for a changing magnetic field will give you what? An electric field. Okay, a changing electric field, or let's say rotating electric field in the opposite direction. That's why I have a minus sign. Okay, so now let's substitute these guys into it. But is there charge density here? No, leave that. Is there current here? No, leave that. No conduction current. Now for this guy, let's replace this guy. Where you have B, you just put this. So this guy should be what? Where you have B, plug this guy there. Okay, so let me just write that in the next line. The next line, negative rho, permeability. Okay, good. So this, let's call it equation 1a. Equation 1a. Okay, so next equation. Okay, B. Now, changing magnetic field, rotating magnetic field equals what? Changing electric field. Changing electric field. Oh boy, what's happening? Changing electric field. Okay, and of course you add the permeability, and then the permeability, and then what? Permittivity, and then your current, and then current I or J. Okay, so let's work with the J, because J is what we have there, and then permeability. Okay, good. Now, do we have current here? We have it here. So where you have current, you put this. Are you seeing it now? Place that where you have current, and where you have this, you place this. So let's do that now. So that will give us what? This, right? And then this, where you have current, you place what? You place this. Okay, okay, good. Now, what we need is this magnetic field intensity, not permeability multiplied by this. So we are going to divide through to cancel out that permeability. Okay, so this will cancel. Of course, we divide everywhere. Permeability, cancel. Permeability, cancel. Okay, so what will be left is just, what we have left will just be this, and then this, and then this, plus this, and then this, all over this. Good. All right, so call this equation 1b. Equation 1b. Okay, so the next Maxwell's equation, the dots equals what? Charge density. So this is the, okay, Gauss law. Charge density over what? This. But our charge density is what? 0. So that will give us what here? Equals oh boy, equals 0 over this. That will give us 0. So that means this guy, that this equals 0. Call this equation what? 1c. 1c. Okay, or I should have done the other one first, and whichever way. Then the next one, magnetism. Okay, this is what? Equals 0 already now. Equals 0. And of course, where you have that, you can put this. The law of magnetism equals 0. We've done that in the previous video, so please watch the previous videos so we don't repeat the whole thing. Of course, when you divide both sides by this, you still get what? 0. So that will give you what? That will give you A. That will give you this equals what? 0. Call this equation what? 1c. Now, I know we already have 1c here, so let's take this one down. I want it to be uniform, so that uniform in the sense that it should be the same with what? The same or at least close. So that when I say equation this, to be the same with what we all have in our notes. So you don't get confused when I'm making reference to equation whatever. So this will be equation 1d. Okay? Equation 1d. Good. Now we have the equations required to derive the wave equation. Okay? Good. 1 A, B, C, and D. Okay, so from this point, to derive the wave equation for the electric field, what we'll do is this. Looking at this, 1 A, 1 B, where is 1 A? 1 A, 1 A, 1 B, 1 C, and then 1 D under. Which one has the electric field? So we can see there's electric field here in 1A, there's electric field in 1D. But of course, the one in 1D equals 0. So, of course, just forget about that. But the one in 1A equals something. The one in 1A equals something. So we are going to make use of that. So you take that, and what do? Remember we said something in the last video that there's a vector identity like this. Okay? Vector identity like this. Either V or sometimes you see A in a textbook. Like different textbook. Okay? Some textbook you see A instead. And it equals what? Equals this. Equals this. The one we dot is inside. Let's go with the A. Okay, minus this squared this. Okay, so we have this vector identity. Now looking at this guy here, well, this guy, if we take the coil, which is adding nabla cross, if we take the coil, this part will look exactly like this. That is, if we do this, take the coil of this. Now this guy looks like this. Are we seeing it now? But of course, what you do to one side of the equality sign, you should also do to the other side. So, for the sake of simplicity, or to simplify this equation 1A, or I should have done that here. To simplify equation 1A, what we'll do, we take the coil of both sides, okay, so that we can get to this identity. So, we'll do that right here, which is this. For the electric field, take the coil of equation 1A, which is what we have just done. Okay? We're having this. Now, of course, we just left this part like this. We didn't simplify this part. The right hand side, look at it. Look at it. This guy is what we have now. Now, having this thing inside, it looks exactly with what we have in equation what? 1B. Look at equation 1B. Nabla cross the electric field. That's the coil of the coil of the magnetic field. Now we can see that this is the what we have for magnetic field. So we'll copy all this and substitute it into this guy. So where you have this guy, bring all that one here. I was seeing it now. So you just open the brackets here. This multiply this. You see, conductivity multiplied by electric field multiplied by this will give you all this. Okay, mu, look at it, which is a permeability, look at it, conductivity, look at it, electric field, look at it, partial this. Okay, now of course when this minus sign multiply this sign, it becomes minus also. So permeability, look at it, at this twin, yeah, permeability, at that here. So permeability, look at it. This guy, permittivity, look at it. Partial multiplied partial give you partial square. Electric field, look at it. And these guys give you partial t squared. Okay, so that's for electric field. Okay. Then for the magnetic field also, same thing. We'll go to the equations. Which one do we have magnetic field? We have it here and we have it here. But for this part, it's equal to 0. This part is equal to something. So we work with this guy. Of course, the same process we did for the electric field, we'll do that for the magnetic field. Taking the coil of both sides. So we take the coil of this. We have something here. We take the coil of it. We have something here. We take the coil of it. Okay? Just like if you want to divide both sides by something, you will do everything. Let me just zoom in and show you. This is one term. This is equality sign, and this is one term. Equal to this term, and it's also equal to this term. Are we saying it? So when you take the coil of both sides, you are taking the coil of all the terms. You have this thing, you take the coil of this, that means you now have nabla cross this, nabla cross this. There is one term here plus another term. So you take the nabla cross of this, that's the coil of that, also the coil of this. Very important, very important. Okay, all right, so let's continue. So that's what we did and arrived at this. Are we saying it? That's what we did. No, this is electric field. That's what we did and arrived at this. Are we together? So the next thing, we left this part like that. The next thing is this. What is nabla cross E? Go back to equation 1a. Where are you? Equation 1a. Look at it. This is nabla cross E. So anywhere you see nabla cross E, you take this thing and substitute it there. So we've done that. Please, you can follow up with your maybe rough note or something. So yeah. So nabla cross E, we place this. Nabla cross E, we place this. Are we together? Then we simply open the bracket. This multiply this will give you this expression. You look at it. You look at it. The rest is look at them. Good. Plus, but we have a minus sign here. When this multiplies that minus sign times plus will give us a minus here. This, look at it. This, look at it. This guy multiply this guy will make it squared. And then we have the h here. Okay. And then this multiply this will give us this squared. Now look at the electric and magnetic, the wave equation for electric and magnetic field. They are both the same, just difference in vector notation. Electric field, electric field, electric field. Magnetic field, magnetic field, magnetic field. The rest things are the same. Next, you know I have not expressed or I have not simplified the left hand side, but we have a vector identity. There's a vector identity which you can use to simplify this side, which we did in the previous video, like we did it well in the previous video. Okay, we explained it. So, but I just wrote it down here again, which is this. Okay, so where you have this expression, you put in this. And of course, please just watch the previous video so I don't make this one too long on the same thing I've explained in the previous one. So when you put in that vector identity, which is this vector identity, and you substitute in nabla dot, you get this. Same applies for the h. Okay, so this is what we'll be working with. Now, since we already have these parts, this is the vector, right? Vector E. This is a vector h. Now the scalar components of the vector, when I say scalar components, I just mean in the x direction, in y direction, and z direction. So for these guys, the scalar component will be this. In the x direction, you just put ex. So anywhere you see e in the formula, you just put ex. So for the y direction, the y component, you have ey. Where you have e, we just put ey. As simple as that. Okay, just substitute that into the equation and z. Also for h, the scalar component for h, you just have hx. Then where you have h in the formula, you put hx. For the y component, same thing. Z component, same thing. Okay, note that we could have just taken this out because we have minus sign everywhere now, so this minus can just cancel out. So everything will just be positive. Or let me just leave that for now. But note that the minus sign can cancel out, and they should cancel out. Okay, so let's continue. Okay, hope we are clear with that so far. Now, before we talk about the next, let me do this right here. Look at this. Now, if you have a simple wave like this, the sinusoidal wave, now you have it like this. Now, imagine a particular point. Now, this point is moving, going like this. Are we seeing it? Now, at this point, you can see, you can trace it back to this line. When it's at this point, you can trace it to this line. When it's at the peak, you can trace it to this part. When it's here, you can trace it back. When it's here, you can trace it. I believe you see what's going on. Okay, so at the different points, if you decide to draw an arrow at the different points where it is, if you decide to draw an arrow when it's at this point, where down, when it's at this point, back. I hope we are seeing what's going on. So at different points, we can trace that line back to this vertical, to the vertical line, and we can form an arrow with that. And that arrow we form, will create an angle here. Okay, we create an angle here. I hope you guys are getting this thing. I hope I had a better way to explain this. But just know that what I'm saying, or what I'm trying to point out, is that at different points in the curve, okay, at different points in the curve, you can trace it back. You can trace it back to this the vertical line. And actually, if you think of it, this will give you a circle. This will give you a circle. Look at it. The highest point, the lowest point. Highest point and the lowest point, that will give you a circle. So at any point, you can trace it back to this, and that forms an angle. Okay? So this point, if we pick two different points, see this point, and this point, are they in phase with each other? Meaning, as this red point is going like this other point will be going like this. So their angles, are they the same? Of course not. Because while this guy, the angle of the red point is changing, okay, let's, at this point, this is the angle for the red point, and this is the angle for this orange point. Are they the same angles? Nope. They don't form the same angle. So as the curve is going, and we are tracing the path, the circular path, as we're tracing the path, we see that the angles are different. This representing it in this, so since the angles are different, we say they are out of phase. Assuming we have them like same angle, then we can say they are in phase with each other. Okay, so this idea of representing this wave, representing the wave in phasor form, we are going to say the change with respect to time, let's represent that with what? J omega. So this is representing it in phasor form now. Okay, so come back here and say we can represent the wave equation in phasor form by replacing partial derivative with J omega. Okay, and that's of course the complex form. So anywhere you see this guy, as you can see, I've removed the minus sign here because they can cancel through. You see minus everywhere now, so they cancel out. So anywhere you see a partial derivative, or when you see derivative, you replace it with what? J omega. Are we together? So you see these guys, of course, look at them. Partial derivative, you put J omega. E, you put E. Sorry, I'm using the one for, let me just do it here, but it's the same thing anyway, just replace the E with H. So where you have this guy, I'll put what? I'll put J omega. Where you have this guy, I'll put what? J omega, but it is squared, so squared. Okay, and then you just plug in the restings. All right, already I've told you that the minus sign cancel out, so this is what you will have. Which is exactly what we have right here. Okay, exactly what we have right here. Now, and of course, you can just factor out what's common. We have permeability here. We have j omega, we have j omega. So when you factor it out, j omega is out, permeability is out. What will be left in this expression? You have what left? Only conductivity left. Plus, of course, you have E left also, but I just put the E at the ending. Okay? So, this other side, what do you have left? J omega, you have one of the j omega. And then you have permittivity here. Okay? So, yeah. So, you have this. Now, also for H. Okay? Just that where you have E, you put H. Where you have electric field, you put what? Magnetic field. Now, you see that all these, they are constants. However, they are constant, but what? A complex number. The constant here is a complex number. You can see J now. You can see the J. So that indicates a complex number. And how do you write a complex number? You have the real part and you have the imaginary part. The real part and imaginary part. So since this is a constant, but not just any number, a complex number. So let's use a gamma to represent it. Gamma. So gamma equals, gamma in this case now we say it's a complex number, right? So gamma is what? Equals the real part, let's use alpha for that, plus the imaginary part, which is j beta. Now, how do you get the magnitude of a complex number? We've done that, not in this video though, but the magnitude of a complex number, you get that by using that Pythagoras stuff. And the real part, and then the imaginary part. Okay, so of course you do that Pythagoras theorem, which will give you this. Okay, and this plus this. Okay, Pythagoras theorem. So we are taking this as the so this is a complex number. So the magnitude of the complex number will be the square root of this. Okay. Now we are not taking the square. We are not putting this. We are not putting this square, square or plus whatever, because all these things, all this square plus everything, we are saying they are equal to what? This guy. So just pack all this and put it inside here and put your square roots. Okay. So this is your complex number gamma. So if you remove this square root and bring it to this other side, it becomes just square. So gamma square equals everything we have here. Okay. So instead of writing these things, you just put gamma square. Just put gamma square, which is this gamma square. Thus, Laplacian of the electric field, which is nabla square of the electric field, equals gamma squared of the electric field. Okay, so the x, for the x component of the electric field, you just express this, meaning everything will be x, x, x. However, partial square x over partial x squared over partial y squared over partial z squared. Go for the y components in the electric field. Then you now say y component, y component, y component, but what? X, y, z. Okay, with respect to x, y, z. Same for z component. Similarly, for the magnetic field, you do exactly the same thing. Okay, so let's just quickly consider the electric field. Then this electric field. So assuming the direction of it to be in the positive x direction. So this electric field, let's assume that it's in what? Look at the sign for direction. It's in the x direction. Okay, so assuming that it's in the x direction and it has what? Z components. Okay, so what does so when we say it's traveling the x direction with z components, let's do this. So let's call this x, okay, and then let's call this z, and let's call this y. Okay, now when we say it's traveling in the x direction, meaning the wave is moving in this direction. Follow my hand, yeah, it's moving in what? In this direction. and it has Z component, you can see that the amplitude, the amplitude, yeah, it has this, there will be a value here, okay, and there will also be a value here. So it has values that's changing in the Z component. It will have a value here, it will have a value here, at this point, like it will have different values in the what, and like, so it has Z component. That's what we mean by it has Z component, because we have values. The highest point, measure it. The lowest point, measure it. At this point, measure it. But in which direction? In X direction. It's moving in X direction. Okay? So that's what we mean by that. Now, Now, recall that from Faraday's law, Faraday's law of induction in Maxwell's equation, we have it like this. We've done this over and over again. We have it like this. And to represent it in phasor form, we remove these guys and put what? J omega. So that's why we have here J omega equals this. Now, recall that to determine the coil of a vector, you can do that using the determinant method, like matrix form. So we express this thing in matrix form, saying that this is for the X, Y, and Z, and of course, plus, minus, plus. Okay? So partial X, partial Y, partial Z, with the X component, Y component, and Z component of the electric field. So once you do that, and how do you do that? For your first part, which is this part, block out all these guys, and you take this. So you say this multiplied by this, which is what we have here, okay, minus this multiplied by this, which is what we have here. Can we see that? Y, put it here, EY over this over this. Can we see that? Clear, right? So when you do that, of course you put this EX here, accomplished. Then you put this minus sign, you place it here, and you repeat the process. Repeat the process. Okay, by saying this guy now, we are at this point now, which is this. They will now say you block like this and you block like this. Then what do you have? You say this multiplied by this, which will give you this guy, minus this multiplied by this, which will give you this guy. Okay, hope that's clear enough. Then you'd also do that for the last one. You do that for the last one. Let's take this out, take that out. Get out. So for the last one, we say we're taking this guy. So also, where are you? Yeah, which is this guy. Okay, so you now block this part, and then this multiplied by this, which is this. Then the last one, this multiplied by this. Of course, you put the minus, which will now give you this. Okay, so you've gotten that expression out there. Let's clear this, guys. Clear. Alright, good. Now, what we'll do, and it's kind of something like good to do. So we just have everything positive. And how do we do that? This minus sign, use it to multiply what you have inside. So minus multiply this, here will become what? Minus. So we just shift the minus this way. So you see minus, when this minus multiply this, here will become what? Minus EZ, this, which is what we have here. When this minus multiply this minus, here will become what? Plus. So we just bring it this way. So you now have EX over this. So you have it this way. So now you can peacefully turn this to positive. Not really turning like turn, but this multiply makes here minus. So we'll bring the minus one this way. This multiply makes here plus. So we'll bring the plus this way. So here becomes plus. Clear? The rest part remains the same. Now, since we are considering the electric field in what? X direction with Z components. Look at this. anything that's not x, is anything that is not in the x direction and is not having the z component, cancel it, because we don't have anything to do with that. So let's check. Is this first one, is this in the x direction? Of course not, so bye bye. Is this in the x direction? Of course not, bye bye. Are we seeing what's happening? Is this in the x direction? Yes. Does it have the z component? Yes. So we leave it. Okay.
So for this, is it ex? No. So out. Next, is this ex? Nope. So out. Next, is this ex? Yes. But does it have the z component? No. So out. Okay. So finally, what we have left is this. So that will be this. All these parts will give us 0. All this results in 0. Okay, that results in 0. And then this, what we have left, it will be this guy. Okay, and of course everything here will be what? 0. Okay, on this, or will be this. Okay, which is also the same as negative j omega mu. Okay, so we'll stop here in this video. Okay, we'll stop here. So yeah, we'll stop here in this video. So thanks a lot for watching. We've done a lot, like really a lot. So please like, share, subscribe, comment, and I'll see you in the next video. Bye for now.